Did you know that a simple drought in the Panama region could cease the operation of the Great Panama Canal? This vital artery of global trade depends entirely on fresh water to move ships across the continents. This marvel of civil engineering uses a clever locking arrangement to lift passing ships by almost 20 meters. The system uses gravity to move millions of gallons of water, safely transporting vessels across the canal. To materialize this smart canal lock system, a super-fast concreting technology was needed. Look at the giant T-cranes the American engineers invented. They were moved by massive rail tracks. These machines allowed for unprecedented speed, pouring thousands of cubic yards of concrete every day. It was a monumental effort involving tens of thousands of workers from all over the world. The result was one of the greatest engineering triumphs of the 20th century, changing global shipping forever. But today, that legacy is under threat. As rainfall patterns change, Gatun Lake's levels are dropping to critical lows. Low water means ships must carry less cargo, increasing costs and disrupting the global supply chain. The Panama Canal is more than just a shortcut. It's a testament to human ingenuity. But it also reminds us of our dependence on nature. Today, engineers are once again looking for solutions, from water-saving basins to new reservoirs, to ensure the canal stays operational. As we face a changing climate, the question is, can our engineering keep up with a world that is moving faster than ever? By investing in sustainable infrastructure and reforestation, Panama aims to protect its most precious resource for generations to come. The story of the Panama Canal is far from over. It is a story of constant adaptation in the face of the unknown. Did you know that the Panama Canal wasn't just a triumph of diplomacy, but a revolution of steam? While the French attempt faltered in the dense jungles, the Americans brought in a new kind of power. They deployed massive steam-powered machines that reshaped the Earth itself, starting with incredible cranes. Look at this. Did you notice that small house sitting above the crane? That's where the magic happened. Inside, a powerful steam engine was the heart of the operation, providing constant, reliable force. It didn't just lift buckets filled with concrete, it controlled every movement with surgical accuracy. This steam-powered cable pulley mechanism was a game-changer for the massive canal construction. It delivered materials to their destination far faster than any manual crew could ever hope. And notice how it moves. This 100-year-old invention could maneuver in all three directions: up, down, left, right, and forward, providing a level of versatility that was truly ahead of its time. But it wasn't just cranes. The Americans deployed over 100 railroad-mounted steam shovels. Like the massive 95-ton Bucyrus, these giants were the most powerful machines ever built at the time. These giants carved out the famous Culebra Cut, moving millions of cubic yards of rock and dirt. The volume of excavation was staggering, equivalent to digging a hole through the entire world. But why was this canal project so important? Why go through all this incredible effort? Because the result changed global trade forever by connecting the Atlantic and Pacific Oceans. Ships could finally bypass the treacherous journey around Cape Horn, saving 20,000 kilometers. This narrow region became the most important shortcut in human history, bridging the world. Even today, the legacy of this engineering marvel lives on in every ship that passes through. From floating giants like the Titan crane to the sophisticated locks we use now, steam was the start. The Panama Canal remains a testament to what happens when human ingenuity meets raw power. Every modern advancement here stands on the shoulders of those first steam-powered giants, an engineering miracle, powered by the revolution of steam. Welcome! Today we're exploring the Panama Canal, a stunning country with rugged terrain that posed a massive engineering challenge. The French tried to dig a sea-level canal in 1892, but landslides and disease led to a tragic failure. After 8 years and 22,000 lives lost, the project was abandoned. Then, the Americans had a brilliant idea. Don't dig the whole mountain, just flood a portion of it. By using massive locks as water elevators, they could raise ships to an elevated lake. This solution filled only a small width with water without flooding the entire country. Today, it remains a marvel of human ingenuity, connecting our world more efficiently than ever before. Thanks for watching this look at the engineering miracle of Panama. See you next time. The Panama Canal is an engineering marvel, allowing ships to traverse the continent. But how exactly did they make it possible to raise a heavy ship to this new water level? Lifting a vessel weighing hundreds of thousands of tons over a mountain range seems impossible. Yet, the solution is surprisingly elegant and relies on a simple trick. Engineers relied on this. If an object can float on water just by increasing the water level, it will be lifted up. It's the basic principle of buoyancy. By controlling the volume of water in a confined space, we can control the vertical position of the ship, lifting it like an elevator. To implement this, we must first install 3 gates at the entrance. These gates act as the boundaries for our lifting chambers, or locks. These chambers are like steps on a giant water staircase, each one progressively higher than the last. Let's look at how a ship climbs them. Assume the first gate is open. The ship enters the region between the 2 gates. Once inside, we close the first gate behind it. The ship is now isolated. Now, we open a valve. This process doesn't require pumps. It's powered entirely by the force of gravity. Water from the second chamber is released into the first. Because the second chamber is higher, the water naturally flows down to fill the first. Both the water level and the ship will automatically rise. It's a slow, powerful movement as thousands of tons are lifted by the rising tide. Once the water levels are equal, the pressure is balanced. Now, we open the second gate so that the ship can effortlessly enter the next chamber. The ship moves forward, having completed the first step of its climb. Now we close the second gate and do one more water leveling. We repeat the process using water from the third, even higher chamber. After a few more water levelings, the ship has climbed the staircase. The ship clears the final lock and enters the expansive Gatun Lake, now 85 feet above sea level. It's now ready to cross the isthmus on its way to the other side. Just like that, the ship continues its journey through this fantastic shortcut through Panama, saving weeks of travel time. This system has been operational for over a century, a testament to the vision and hard work of the engineers who built this wonder. The canal remains a vital artery for global trade, connecting our world and making the impossible possible through the power of physics. Thanks for joining us on this journey through the Panama Canal. Stay curious and keep exploring the wonders of human ingenuity. When a ship reaches the end of the Panama Canal, it faces a final engineering hurdle, returning to sea level. This is achieved through a precise water leveling sequence, moving the ship down step by step. The entire system is powered by gravity. No external pumps are used to raise or lower these massive vessels. However, this method creates a water step. To let the next ship in, this extra water must be released into the ocean. That water comes directly from Gatun Lake. With every ship that passes, the lake loses a massive volume. The lake stays full thanks to the surrounding rainforest, which acts as a natural sponge for rainfall. Newer locks now use recycling basins to preserve this precious water for future transits. The Panama Canal is a masterclass in working with nature rather than against it. It's a gravity-powered miracle that continues to keep the world connected. Thanks for joining me. The Panama Canal is a marvel of engineering, but its most critical component isn't steel, it's water. Without Gatun Lake, operations would cease. Gatun Lake is supplied by the Chagres River, fed by intense tropical rainfall. As long as the rain falls, the canal's cycles are maintained. However, the 2019 drought was a wake-up call. Low water levels forced shippers to limit cargo just to navigate the waterway safely. The following year brought back the rain, and with it, the canal's full capacity. But the lesson remained. Water is the lifeblood of trade. Today, innovation drives the canal's future. From water-saving basins to reforestation, every effort is made to protect this vital resource. The story of the Panama Canal is one of adaptation and respect for nature. Together, we can ensure its survival for generations to come. Thanks for watching. The construction of the Panama Canal was one of the greatest engineering feats in human history, requiring unprecedented solutions to geographical challenges. To connect the Atlantic and Pacific, engineers had to tackle the massive elevation changes and the volatile Chagres River. To manage this, we must first construct a dam. The water stream from the Chagres River will accumulate within the dam region. The newly formed water body is called Gatun Lake, one of the largest man-made lakes in existence at its time. Simply by controlling the dam height or the height of the water surface, we can achieve different levels of flooding. Unfortunately, there is no way to flood only this region. If you try to flood the entire crossing, almost the entire country of Panama would be underwater. Because of this, American engineers decided to stop the flooding at this level. Almost 2/3 of the land is flooded. Only a small portion remains above water. Now begins the real challenge, the removal of this 15-kilometer-long unflooded region. This is the formation of the Culebra Cut, the whole purpose to connect the dam and the ocean water. Have a look at these gigantic machines, known as a track shifter, dirt spreader, and unloader. Each played a vital role. Interestingly, these machines allowed for a pace of excavation that was previously thought impossible in such harsh conditions. The engineering team faced constant landslides and tropical diseases, but they persevered, carving through the continental divide. This monumental effort changed global trade forever. The Panama Canal remains a testament to human ingenuity. Join us next time as we dive deeper into the world's greatest engineering marvels. The construction of the Panama Canal was one of the greatest engineering feats in history, but it required revolutionary machinery to succeed. The most difficult section was the Culebra Cut. The goal was simple but daunting: remove the earth to connect the Atlantic and Pacific Oceans. The king of the Panama Canal construction machinery was the steam shovel, specifically the massive units created by the Bucyrus Company. To accomplish this mega project, 70 such steam shovels were employed, working day and night to carve through the mountains. But even such a gigantic machine struggled in Panama's unforgiving rocky terrain. The machines alone weren't enough. The right solution was the strategic and massive usage of dynamite to break the Earth's resistance. A staggering 800,000 sticks of dynamite were used on average per month during the major excavation work. The dynamite effortlessly broke large, stubborn rocks into smaller pieces that the mechanical giants could handle. These fragments could then be easily scooped up by the steam shovels, speeding up the process significantly. With every single movement, one scoop could move 2 tons of dirt. The efficiency was unparalleled for its time. The way the dirt was dumped into the trains was a marvel of logistics, a constant flow of removal that never stopped. Now, take a look at the true power source of this gigantic machine: the steam engine. It was the heart of the entire operation. The way this steam engine translated pressure into raw mechanical force allowed humans to reshape the very face of the planet. The environment was just as challenging as the rock. Rain, mud, and heat tested both the men and their machines every day. Through the mud and the storms, the steam and steel pushed forward, slowly but surely carving the path. Operating these giants was a precision task. It required experienced hands to maneuver 2 tons of rock with such accuracy. The scale of logistics was unprecedented. Millions of cubic yards of earth were transported, shifting the geography of the isthmus. Behind every machine were thousands of workers whose sweat and labor made the mechanical dream a reality. The innovations developed here laid the groundwork for modern construction technology that we still use today. The result was the completed Culebra Cut, the crown jewel of the canal, finally allowing the oceans to meet. The legacy of these massive machines lives on in the canal's continued operation over a century later. The Panama Canal remains a testament to human ingenuity and the power of the machines that built it. Thanks for watching this look at the giants of Culebra. The construction of the Panama Canal was more than a feat of labor. It was a triumph of mechanical engineering. At the heart of this massive excavation were the steam shovels, monsters of steel that redefined what was possible. The controls of these machines were classic examples of the incredible innovations of the early 20th century. Engineers turned the boom using a mount with a rope around it, allowing for precise lateral movement. This simple yet powerful mechanism enabled the shovels to sweep across the excavation site with ease. The dipper stick was able to move to and fro thanks to this interesting gear arrangement, providing depth to every scoop. This reach was crucial for clearing the massive volume of earth required for the canal's deep cuts. The dipper stick could also rotate because of this chain pulley arrangement, giving the operator full control. Every movement was a mechanical symphony, coordinated by skilled operators in the thick of the dust. When the bucket was ready to dump the material, the crane operator simply pulled the latch. The heavy doors would swing open and gravity would do the rest, filling the transport wagons. The wagons, now filled with dirt, could start their journey towards the dump area. But transporting the earth was only half the battle. Getting it off the wagons was the next great hurdle. As it turns out, even just emptying the dirt from these 20-plus wagons was a massive logistical challenge. Manual labor simply couldn't keep up with the pace of the steam shovels. A new solution was needed. With the help of an experiment, let's see how Americans solved this issue using simple mechanical principles. This simple piece solved the big issue of unloading. It was essentially a massive plow pulled by a cable. By pulling this plow across the entire length of the train, an entire load could be cleared in minutes. Let's see it in action. I am moving the unloader piece along the track. You can see all the stones are falling down in this direction, clearing the wagons effortlessly. The speed was incomparable. What took hours for a crew of men now took mere seconds. In the field, this meant the canal could grow at an unprecedented rate, day after day. These innovations didn't just dig a canal, they built the foundation for modern heavy machinery. It was the perfect marriage of human ingenuity and mechanical power. Today, we look back at these machines as the ancestors of our modern world. The story of the Panama Canal is a testament to how we solve impossible problems with simple, brilliant ideas. From the rotation of a dipper stick to the sweep of an unloader, every detail mattered in changing the map of the world. It's amazing to think that these early 20th century solutions still influence how we move the Earth today. Thanks for joining me on this journey into the mechanical heart of history. I'll see you in the next one. In the massive excavation of the Culebra Cut, moving millions of tons of earth was the primary challenge. The Americans developed an industrial-scale system of logistics and machinery to tackle this monumental task. This effort required thousands of workers and hundreds of locomotives working in perfect synchronization. Before the soil could be moved, it had to be dug. Over 100 massive steam shovels were deployed, each capable of lifting 8 tons of rock in a single scoop. When the earth was too hard, tons of dynamite were used to blast through the rock, turning mountains into rubble for the shovels to collect. At the heart of the transportation effort was the automated soil dumping machine, powered by a massive steam winch. When the winch rotates, it pulls a heavy plow known as a Lidgerwood unloader across the entire length of the train. As the unloader moves, the soil is dumped from the open edge of the wagon in a continuous, powerful stream. This ingenious system allowed an entire train of 20 cars to be emptied in just a few minutes, clearing the way for the next load. However, this efficiency created a new bottleneck, massive mountains of dirt accumulating on the sides of the track. These growing piles would soon block the next arriving wagon, threatening to bring the entire excavation to a halt. To solve this, the Americans invented the dirt spreader, a specialized machine designed to clear and level the dumping areas. It featured large steel wings that could extend 11 to 13 feet on either side of the rails, operated by compressed air. Watching the spreader in action is incredibly satisfying, as it clears tons of earth in a single pass with unstoppable force. It effortlessly flattens the dirt mountains, widening the embankments to accommodate even more tracks for the construction. Once the embankment was wide enough, the tracks needed to be moved to the new, flat surface to keep the trains close to the digging face. Shifting miles of heavy rail manually was far too slow for the project's ambitious timeline, requiring hundreds of men for minimal progress. The solution was the track shifter, a machine capable of lifting and moving entire sections of track at once. This machine could lift an entire section of track with its rails and ties still attached, moving it as a single unit. It worked like a giant crane, swinging the track several feet to its new position with remarkable mechanical precision. These specialized machines were the unsung heroes of the Panama Canal, transforming the landscape and making the impossible possible. Join us next time as we explore more engineering marvels. The construction of the Panama Canal was an engineering feat defined by impossible challenges and the machines that solved them. Before the invention of specialized machinery, moving railroad tracks was a grueling, labor-intensive process that slowed progress to a crawl. To overcome this, engineers deployed a genius piece of technology, the track shifter. This machine featured a small but powerful crane, driven entirely by the power of a nearby locomotive. Skilled workers would connect the track to the shifter, preparing for a maneuver that would revolutionize the dig. The first step in the operation was to lift the track completely off the ground. This was achieved with a precise chain yoke and upper boom arrangement. You might wonder how these heavy steel rails could bend so dramatically without breaking. This was possible due to the use of a special kind of flexible steel rail designed specifically for this purpose. Next, the lower boom turns toward one side, and the entire section of track is shifted laterally in one fluid motion. This allowed a large section of track to be repositioned without the need to disassemble and rebuild it piece by piece. Without this invention, it would have required an army of around 500 workers toiling under the old method. Shifting every tie and rail separately was a logistical nightmare. By using this newly invented machine, the efficiency of the American project skyrocketed. The track shifter became the unsung hero of the canal. Today, the Panama Canal stands as a testament to these early innovations. The track shifter's legacy is etched into every mile of this historic waterway. Thanks for joining us for this look at the machines that built history. I'm your host, and we'll see you in the next deep dive into the engineering wonders of the world. The construction of the Panama Canal was an engineering feat that redefined global trade, but one segment stood above all as the ultimate challenge: the Culebra Cut. Through careful planning and the deployment of massive machinery, the government saved several $1 million. Now, it's time to see how the engineers formed this cut. The machines used were unlike anything seen before. Their power was essential to carving through the continental divide. The Culebra Cut was a big engineering lesson for civil engineers worldwide, teaching them about the limits of human ambition and the power of geology. Suppose the excavation took place in a non-mountainous region. This narrow profile is what the French thought was sufficient to dig. However, nearly 3 times more soil needed to be removed. Even the Americans couldn't imagine the need for such a massive amount. The reason for this was landslides. Every time they dug deeper, the unstable earth above simply slid back into the channel. The culprit was the angle of repose. All materials have a specific angle at which they remain stable without sliding. The angle of repose needed for the Culebra region was quite low. To achieve a stable cut, they had to widen the entire top of the hills. For years, the work continued. Millions of cubic yards of earth were hauled away by a relentless network of trains and shovels. Day after day, the cut grew wider and deeper as engineers fought the very geography of the isthmus. It was a war of attrition against the earth itself. After years of relentless removal, the Culebra Cut was almost ready. The last challenge remaining was this heightened portion called the Gamboa Dike. It held back the waters of Gatun Lake from the dry cut. As you might expect by now, the Americans tackled this issue in style. With a single massive explosion, the waters were let in. Today, the Culebra Cut stands as a testament to perseverance. It is a reminder that engineering isn't just about building up, it's about the patient, calculated removal of obstacles. Thank you for joining us on this journey through the history of the Panama Canal. I'm your host, and we'll see you in the next chapter. On October 10, 1913, a single spark changed the course of global trade forever. In Washington, D.C., President Woodrow Wilson pressed a button, sending a historic signal across the globe. This signal traveled through an extensive electrical cable network, spanning over 6,000 kilometers, mostly beneath the ocean floor. At the other end, 7,000 kilograms of dynamite waited at the Gamboa Dike, the last barrier between 2 mighty oceans. 4 seconds after the button was pressed, a massive explosion tore through the dike, leaving a 60-foot gap. The waters of Gatun Lake immediately rushed to the Culebra Cut. At last, the Atlantic and Pacific Oceans met. It was a moment of immense pride for Americans, and a milestone the entire world celebrated. But how does this marvel of engineering actually work today? Let's review the details of a ship's transit. The journey begins at the locks, where ships are lifted 85 feet above sea level to the height of the lake. Gravity-fed water fills the chambers, acting as a massive aquatic elevator for the world's largest vessels. Electric locomotives, known as mules, maintain precise control, ensuring the ships stay centered in the tight chambers. Once lifted, ships navigate the vast Gatun Lake, a critical reservoir that powers the entire lock system. They then enter the Culebra Cut, the most challenging section to excavate due to constant landslides and solid rock. At the Pedro Miguel locks, the descent begins. One chamber drops the ship 31 feet. The final 2 steps happen at Miraflores, lowering the vessel back to sea level. Every transit requires millions of gallons of fresh water, highlighting the canal's dependence on the local ecosystem. The canal is not just a shortcut, it's the heartbeat of Panama and a pillar of the global economy. Today, satellite navigation and advanced computer systems manage the complex flow of traffic. Protecting the surrounding forests is now as critical as maintaining the machinery itself. The 2016 expansion ensured the canal remains relevant for the new generation of megaships. From a single spark in 1913 to a digital masterpiece of logistics, the Panama Canal continues to defy the odds. It remains a testament to human ingenuity and the power of connection across continents. I hope this journey through history and engineering has been as fascinating for you as it was for the world over a century ago. Thanks for watching. At the Panama Canal, cargo ships must turn off their propellers when nearing the locks. They are guided by tugboats and then tethered to electric locomotives called mules. These mules travel on tracks to perfectly align the ship within the narrow chambers. After climbing the water steps, ships reach Gatun Lake and the famous meter locks, originally designed by Leonardo da Vinci. The genius design of the miter locks forms a watertight joint automatically. To sustain our education service, please support us on Patreon. I would truly appreciate that. Thank you for watching the video. Take care and bye-bye.